All right. So yesterday we started talking about the states of matter. And before we go into answering this question, this is where we left off. So you're going to need to open up your EISN. So take a minute, please. Open up your EISN, ladies and gentlemen. Okay. The new one that I gave you yesterday is the Unit 2 one. Okay. So that's the one that you are looking for. All right. Now, a lot of this should be a review for you. You should have had this when you were in physical science here. Talked about the states of matter. You've probably been talking about them since you were in about 4th or 5th grade for sure, maybe even before that. But we take it a little bit further each time in each year. Ultimately, what determines a state of matter, ladies and gentlemen, is right here. This is what we use to define a state of matter. So if you are looking at an object and you're like, all right, is that a solid, a liquid, or a gas? The two questions that you should ask yourself is ask yourself about its shape. In other words, does that object have a definite shape? Now, definite means a shape that will not change. A shape that holds on to its own. So your computer in front of you right now has a definite shape to it. Okay? If you put it in your backpack, if you put it in your locker, if you put it on your desk, its shape does not change. That is what we mean by definite. Okay? And solids have a definite shape to them. Solids also have what we call a definite volume, meaning they take up a certain amount of space. They are so big. Now, people will say this. Well, Mr. Brand, can't you take and change the shape of something? Okay, if you have a chunk of metal, can't you bend it? Can't you form it? Can't you put it into another shape? The answer there is yes, you can. But what we're talking about here is if you set it somewhere, does it hold the shape that it is in? That pipe, if I take and I put it in another room, if I cut it and put it on a table, if I move it somewhere else, is it going to change its shape on its own? That's a question we are asking. Okay? Now, if I take a hammer and beat the heck out of it, yes, its shape will change. Not the same thing. Okay? So your computer, you could break it and change its shape, but it would still have a definite shape even when you are done. Okay? For a liquid has a definite volume. It takes up a certain amount of space. Every container that has a liquid in it, your juice box to your Gatorade bottle to a bottle of water to the pitchers of water that are up in the back of the room, all have a definite volume of liquid in there. We can see where the water level ends. You can see in this bottle of sanitizer where the liquid sanitizer ends. There is a certain amount in there. That is a definite volume. But what happens with this is this takes the shape of its container. And as you move it around, its shape will change. Okay? A solid will not do that. A solid, you put it in that container, it is not going to change its shape. It's going to stay the same. So, that is the difference between a liquid and a solid. Solid has the definite volume and the definite shape. Liquid has a definite volume, but no definite shape. And then, ladies and gentlemen, there are gases. Now, gases are unique. Gases will take the shape of their container just like a liquid does. You want an example of that? Think about blowing up a balloon. If your balloon is a long, thin balloon, that's the shape that the gas is going to take inside it. If your balloon is round, that is the shape that the gases will take inside it. If it is a Valentine's Day heart-shaped balloon. That is the shape that the gases will take. Whatever that container is, the gases will take the shape of that container. Okay? Well, liquids do that as well. But gases completely fill their container. They take up all of the space that you give them in the container. Here, this water bottle is not full. The water ends here. Why? Because it has a definite volume. It can't just expand and fill up the rest of this space. But a gas can. The gas inside here can expand or contract as needed to fill up the space inside this bottle.
If you just put more water in there, wouldn't it start completely fill it up?
It can, yes. But the water only has a definite volume. You could completely fill this. You are absolutely correct, sir. But it's not going to fill up on its own. Okay? If we had a balloon that was filled with hydrogen sulfide. Hydrogen sulfide is a gas, ladies and gentlemen. Hydrogen sulfide is a gas that smells like rotten eggs. Have you ever smelled rotten eggs? It's a very pungent, very strong scent. If we had a balloon full of that in here right now, you wouldn't even notice it. But if I take it, pop that balloon, you're all going to smell it. Why? That gas is going to completely fill the new container that it's in, which will be this room. It will spread out, and you will all get the wonderful opportunity of experiencing hydrogen sulfide gas. It's not pleasant, okay? But I'll give you a more practical example. Nobody in here, but if you've ever been in a place where somebody either farts or has bad BO, you don't have to be right next to the person to smell it.
What does BO stand for?
Body odor. Some people have bad body odor. Some people just naturally, their glands produce a lot of scents and things, and they can't control it. Sometimes it's because people don't shower. Sometimes it's because they don't wash their hair. Sometimes it's because their clothes may not be clean. My parents both smoked for years. Okay? I could tell their clothes from anybody else's because everything that they owned had the smell of smoke on it. So, again, that scent spreads out everywhere. Okay? If you were to fart right now, everybody in the room would smell it if you did. Why? Because the gas spreads out completely. It takes and fills its entire container.
Sometimes it doesn't smell at all.
You're right, because it depends on what is in the gas when you release it. There are some things that make the gas more smelly and some things that don't. Sometimes people fart and there's no odor to it. Sometimes you fart and there is. Okay? It all depends. Okay? The point is, let's do something a little better then. Have you ever had that person who thinks that Axe body spray is a deodorant? Do you know what I mean? The person who you walk into the room and you're like, oh my God. You could smell the perfume, the body spray, those things on them right away. That's because that gas is spreading out and filling up the entire container. The entire container, whatever room they walk into. So that's just the way gases work. Okay? Now, that's the differences between them. With that in mind, all right, Jell-O. We're talking about Jell-O. You got to pick a state of matter. Solid, liquid, or gas. We will start with solid. How many people think Jell-O has a definite shape and a definite volume? Raise your hand now if you think Jell-O is a solid. No one. All right, how many think Jell-O is a liquid? Now, you are not going to tell me that you think Jell-O is a gas, Alexander. You think Jell-O is a gas? Then what is your only other choice if you didn't vote for the first two now? So let's try this again.
It's both. Like,
You got to pick one. You got to pick one. How many think Jello's a solid? Raise your hand. How many think Jello's a liquid? Raise your hand.
I'll say solid.
Yeah. Does he not understand what we're doing here?
I know.
How many people think it's a solid? No. How many think it's a liquid? I think it's a solid.
I was just thinking about it.
Anybody think it's a gas? Good. It's not a gas. Okay, why is it a liquid, Adon?
Why?
Yep, why?
Because if you stand still, it turns to liquid.
Okay, so if you let it sit there, it'll turn into a liquid. Okay, all right, I'll buy that. Good reason. Jose, which one did you pick?
Liquid.
Why? Adon, we'll come back to you in a second.
Because, like, you need water to make jello.
Okay, you need water to make jello. Okay, fine. Good. Adon, you seem to have like a moment of truth there or something. What did you think? Did you change your mind or?
Nah.
All right, why is it a solid?
I would say it's a solid because it's hard when you hit it, and it's pretty hard to get your hands like out of it. So I would say it would be a solid.
Okay. Jello, by the definitions we gave you, is a solid. It has a definite shape. It holds its shape. You could take it out of a Jello mold and it'll look like whatever mold it was in. And it has a definite volume. Now, really, the difference between a solid and a liquid is, does it have a definite shape? Now, I understand what you're saying, Jose. You use water to make it and things, but we could freeze water, right? And then it is what state of matter?
Solid.
Solid. And I agree with you, Adon. If you leave Jello sitting out long enough, it'll turn to a liquid. Okay? But when it first comes out, I would say it's a solid. I would say it's a solid. All right, how about fire? How about fire?
I would say.
Well, let's start with this. Who thinks it's a solid? Fire is a solid. Who thinks it's a liquid? So we're all going with gas?
Yeah, I think so.
Yes? Why?
Because
Good. Let's finish that sentence.
just like gas, it tries to like fill up its.
Okay. Tries to fill up its space. It'll spread, yes. Okay. Anybody else? Okay, I lied to you. There's a fourth state of matter. Anybody know what the fourth state of matter is? Starts with a P. Plasma. Fire is actually the plasma state of matter. Now, we're not going to talk about it much. Why? Because in chemistry, very few things are plasma. But that's what fire would be. All right, how about energy? What state of matter is energy in? Solid, liquid, or gas?
I'll say no.
Why?
Because energy just it's not it doesn't have a mass.
Good. Somebody remembered the very first unit that we did. In the first unit we did, we said that there are things that are not matter. Energy is not matter. Energy is not something that has mass. Energy is not something that takes up space. Energy is not matter. It would not be any of the three. Does anyone know what I talk about when I say silly putty? That stretchy stuff. When I was a kid, you could take and put it on like the Sunday newspaper, on the comics, and pick it up, and there would be a copy of what you put it on there. Kind of be like, it was almost like a kind of a copy thing. Okay? What state of matter is that? Solid, liquid, or gas? I'm not going to trick you anymore. There are no more plasma ones. There are no more ones that are not one of the three. So what state of matter do you think silly putty is?
A mix of solid and liquid.
Okay,
Right in the middle.
but now remember, it's got to be one or the other. So the question is, does it have a definite volume? Does it take up a certain amount of space?
Yes.
Okay, then we know it's not a gas for sure. Because gases do not have a definite volume. Then the question becomes, does it have a definite shape or is there no definite shape? In other words, think about this. If you leave it sitting there on its own, will it hold its shape?
No.
Or will it just run all over the place?
It'll run all over the place without the liquid.
Nope. Silly putty doesn't run all over the place.
It does though.
You can stretch it. You can pull it. You can move it. But you have to do that to it. You have to do that to it. It doesn't just sit there and kind of go and ooze out all over the place. Right? Silly putty is a solid. Silly putty is a solid. How about glass?
No, that's definitely solid.
Glass.
Solid.
Anyone have anything else? There's actually people who believe glass is a liquid.
I guess
A very, very thick liquid. There are people who say, well, over time, glass from windows get thicker at the bottom than at the top because they say the particles move down. It's not true. Glass is a solid. Glass is a solid. Okay? But there are some people who believe that over time, glass literally starts to move. Now, it takes hundreds of years. And we're talking about real old houses where they will talk about the glass at the top is not as thick as glass at the bottom. And that's not true. If it is, the glass was originally made that way. It didn't transfer over time. Okay? So those are our things there, ladies and gentlemen. All right. I do want to point out a couple of reminders to you, or a reminder to you. We are not doing any unit quiz right now before break. When we come back after break, we'll have a unit quiz on the things that we are talking about now, but we won't do it like the day we come back. We'll do it shortly after we come back. When we do come back, we've probably only got a couple weeks left in this unit, and then we'll be taking the Unit 2 test. If you did poorly on the Unit 1 test and want to do a retake, meaning you got less than a 34 on the Unit 1 test, you can do a retake, but it's got to be done before the next one is completed. Okay? Today we're going to talk a little bit about phase changes, and we're going to talk about something called KMT. So we're going to get through these slides, and then there is a worksheet we'll give you time at the end to work on and get done and be finished with, and then you won't have anything to worry about for today. So let's get through the things we need to get through real quick, ladies and gentlemen, so that you can have some time to work on your homework. All right. So here we go. On the next slide, ladies and gentlemen, the idea of solids and liquids and gas, and what you weren't taught in physical science and what you weren't taught before about solids, liquids, and gases is this. There is a thing called KMT. Now, if I were you, I would write these 2 points down that I'm about to give you on your yellow periodic table because this is a great test question, okay? KMT stands for what is called kinetic molecular theory, okay? Kinetic molecular theory. And this is the basis for how we are going to look at things in chemistry, okay? Now, there are 2 points to KMT. Point number 1, everything around us, all matter, is made up of tiny particles. What do we call these tiny particles that make things up? Atoms and molecules. These are the tiny particles that make things up. Okay? So all matter is made up of tiny particles. So small that you and I cannot see them. So small that you and I cannot see millions of them together. So small that even if we are looking at billions of them, we probably can't even see them with our naked eye. We need to be looking at incredibly large quantities of them. By the way, of atoms, there are only 118 in the world, ladies and gentlemen. Here is a list of every single one of them. There are 118 different elements on the periodic table, and they make up everything around us. And of those 118, only the first 92 occur naturally here on our planet. That you could find them in the ground, in the soil, in the air, in rocks, in minerals, in things like that. Everything from 93 to 118 is man-made in a lab, where we take two small atoms, we get them spinning around incredibly fast, and we slam them together really hard, and then they make a larger atom. And we make elements 93 through 118 in a lab somewhere. Okay? So everything around us is made up of these things, or some combination of these things. That's all of them. There ain't no more. Okay?
Does that mean combining atoms and stuff would make a different type of, I guess, molecules?
Correct.
So there's like
Now, if you look around the room, you could probably see more than 92 different things. Between the wood table, the metal frames, the glass, the different plastics, the posters, the ceiling tiles, probably see more than 92 different things. So yes, these atoms combine to make molecules or compounds, and then they make up most of the things around us. Now, even though there's 92 naturally occurring elements on the periodic table, probably most of the stuff around us is made up of probably 30 or more of those. The rest make up some specialty things, but not a lot of things, okay? In the back of the room back there, ladies and gentlemen, there is a periodic table that kind of shows you what things go into. So what the different elements are used in or can be found in and things like that. So different things can be found in different places.
oh, there's a lot of elements that are used for nuclear.
Yes, there are. Anything over 92 is a radioactive. Yes. Now, here's the other important thing. Those particles that make things up are constantly moving. They are constantly moving. They never stop. Those are the 2 points to kinetic molecular theory. All matter is made up of tiny particles. Those tiny particles are always moving, and hopefully you have that down on your periodic table. Okay? So this is what the 2 points to KMT are. Questions? Now, if I look at this desk right now, is it moving? No, definitely not. Your desk that you're sitting at is not moving. But what is moving are the particles inside this. And because this is a solid, all they're doing is vibrating back and forth. That's all they can do. In the liquid in here, the particles are a little bit more spread out, and they're moving around one another in different areas, bumping into each other, hitting off of each other, moving. But they're able to move a little bit more. That's why if I take and put my finger in a liquid, the particles can spread out, leave room for my finger. And then when I take my finger out, they go back in and fill up the area. These are so close together, I can't get my finger through them. And then there are some particles in the air. The particles in the air are moving away in all different directions. And they keep moving away until they hit something. The thing is, there isn't as much for them to hit because the particles are more spaced out.
I got a question.
Go ahead.
Can atoms actually touch each other or no?
Yeah, all the time. They bump into each other. That's how we get compounds. You cannot make a compound if the two atoms never touch one another. They have to physically bang into each other, and then we have a shot of making a compound.
I was just thinking that they get close enough to transfer energy, but not like actually. I don't even know.
Not energy, electrons. We'll get into that later. Okay? So, but these particles are moving around and they are hitting each other. Now, in your desk, they're hitting each other all the time. Why? Because they can only vibrate back and forth. In a liquid, they're hitting each other all the time. Why? Because they're a little bit more spread out, but they're still in the same basic area. In a gas, they're more spread out. They don't hit each other as often. But they do fly around, okay? And they move around until they hit something. And if there's a particle that's flying right at Fantasia's head right now, it's not going to go around her. It hits her in the head and bounces off in some other direction. Then it could hit me, then it could go hit David, and it's just like pinball all over the place, just bouncing around, okay? That's what's happening with these particles, okay? All right. Now, this explains how energy and matter interact. What happens if you add heat to something? What happens if I add heat to that pipe? What? It might, but I got to add a lot of heat to it, right? How about the flagpole out in front of the school? Think about that for a second. What's the temperature outside today? About? Anybody? 30 degrees I got. 30 degrees. What's the temperature outside in August? In the what? 80s, 90s, right? Does the flagpole melt? No. But what does happen is in summer, the flagpole will heat up. It's hotter in summer than it is right now, correct? What does that mean? That affects the particles. That affects how the particles are moving. The hotter that pole gets, the particles move differently because of it. We will explain how in just a minute. Okay? Now, this should be a review for you. If you need to, again, please write this down. What do we call a solid becoming a liquid? And I will give you a hint. Think about an ice cube becoming water. What do we call that? An ice cube becoming water, Evelyn. If I take an ice cube out of the freezer and hold it in my hand, what is it going to do? It's going to melt. That's the process of melting. Okay? That is the process of melting. There is another scientific term for that, which is fusion. Fusion and melting mean the same thing.
I was about to say transformation.
Nope. Fusion or melting. Now, if we take water and put it on the stove, and we turn it into a gas, like if we were making pasta, what do we call that, Jesus? Water on the stove becoming a vapor, a gas. What would you say the water in the pot is doing? We could, but there's a better term for it. We normally don't say, look, there's a pot of evaporating water. Look, there's a pot of boiling water. I'm just trying to keep it to terms that we're hopefully familiar with. And we could use boiling or we could use what is called vaporization, meaning going to a gas. Okay? Now, does anybody know what it means to go from a solid directly to a gas? Nope. A solid directly to a gas. It's a process we call sublimation. Have you ever heard of dry ice?
Yes.
Do you know why they call it dry ice?
Because it's dry ice.
Okay, but what does that mean? You give me a great definition there, sir, but what does that mean?
It's just gases that have been frozen into it.
It is a solid chunk like ice, but it doesn't go to a liquid state. It goes directly to a gas. Now, there is a great pizza place in Chicago called Lou Malnati's. They make great pizza, deep dish Chicago-style pizza. They will ship it anywhere in the world to you. You still have to bake it when you get it, but they will ship it anywhere in the world. And they pack it in dry ice. Why? If they packed it in regular ice, the ice would do what?
No.
And your pizza would get all soggy. They pack it with dry ice. The solid becomes a gas. Your pizza doesn't get soggy, but it stays frozen until you get it.
I kind of question if you put some kind of food, if you put some kind of like meat or something in dry ice and just leave it there for like centuries, whatever.
No, it will eventually go to a gas. It will eventually go away. But it does it much more slowly than regular ice.
The thing I was just saying was, would the meat like get rotten or something?
No, it does not. It stays frozen. Now again, eventually, you leave meat in the freezer too long, it gets freezer burnt. It isn't good anymore. There is a limit as to how long you can do even frozen things, right? But people who go far away hunting, people who go out west to Montana, to the Dakotas, to Wyoming, to go hunting for elk or boar or whatever they go hunting for, if they shoot something, they have to ship it back to their home. They will pack it in dry ice because, again, it won't melt. It won't make it all watery, things like that. Okay? Different things to use it for. All right, let's start going backwards now. Now if we go from a liquid, take water and make ice out of it, what do we call that process? What do we call if you take water and make ice out of it, Alexander? So you take water and put it into part of your refrigerator at home. You freeze it. You freeze it. Sorry, forgot one more thing. All of these ones on the inside, you'll notice what color are they?
Yellow.
No. What color are the lines?
Blue and red.
What color are the inside lines? Red. What does red represent? If you were at a faucet, what does red represent? Hot. The way we get those things to happen is we add energy. We increase the energy. That makes those things happen. The only way you get ice to melt, water to boil, dry ice to sublimate is you have to add energy to them. Add energy to them. And that process is called being endothermic. Endo means to put into. Thermic means heat. So you're putting heat into something. All right, so now we go the other way. We go from a liquid to a solid. We call it freezing. By the way, you may also hear the term solidify or crystallize. Any of those are terms we use in science to represent that happening. Okay? Now, you take a shower in the morning. You get out of the shower, you open the shower door, you go up to the mirror. What happens to the mirror? Condensation occurs. Condensation occurs. That is a gas becoming a liquid. That is a gas becoming a liquid. So what you've got, ladies and gentlemen, is you've got water vapor in the air from your hot shower, hits the mirror in the bathroom, and starts to condense or become a liquid again. It also happens on a hot summer day. You go and get a soda from McDonald's. You get all the water on the outside of your glass. That is condensation. Okay? The opposite of sublimation is called deposition. Deposition is going directly from a gas to a solid, and that can happen at this time of the year on your car outside. You can get frost that develops on your car outside that comes right from water vapor in the air onto your car. I'm not talking about it snowing. I'm talking about it deposition, frost appearing on grass, appearing on your windshield of your car, freezing right there. Now, what does blue represent in a faucet? So here we're talking about taking away energy. We're talking about energy being given off. When you give off energy, you will go from a gas to a liquid or a liquid to a solid. This is energy being given off. Okay? So that is what we've got there. Questions?
So does that mean gas has energy?
That means the particles in the gas have energy. Remember, KMT, all matter is made up of particles. They are constantly moving. Because they are moving, they have energy. Okay? Questions? All right, we'll give you a minute to finish typing. While we listen to them drill some holes in the wall next door.
What are they making?
They're hanging a TV monitor for me.
Why?
Because I wanted a TV monitor.
In the hallway?
Yes. Why are you looking at me like I'm crazy? I need to watch my ESPN somewhere.
In the hallway?
Yeah.
Okay, yours is lying to me, guys.
I am lying to you about the ESPN, but. All right, we good?
Yep.
All right. All I have done here on this next slide is taken all those definitions and put them into words for you. All I did was take the definitions and put them into words. If somebody asks you what freezing is, it is the process of going from a liquid to a solid. If someone asks you what melting is, it is the process of going from a solid to a liquid. All we've done is taken them and put them in there. But I do want to point out one thing. Jesus, you said this earlier. Evaporation. Evaporation is going from a liquid to a gas, but it only occurs at the liquid surface. That is the only place evaporation occurs. And you do not have to add heat to get evaporation. You have to add heat to get something to boil. You do not have to add heat to get something to evaporate. Okay? So, Some of these are exothermic processes. Some of them are endothermic. By the way I remember that, ladies and gentlemen, if you are leaving something, a building, you go through the what door? The exit. Exothermic energy is leaving. Energy is going out of it. If you are going into a building, that is endothermic. Okay? So going into something, in with energy, endothermic, energy leaving, exothermic. All right. Real quick here. Was this slide filled out for you?
No.
Okay, please copy it down then real quick. I couldn't remember if I did this for you or not. Sorry. Sorry. Nope. There you go. Okay. I just wanted to point out the difference between boiling and evaporation, because in science, definitions matter. And while you may say boiling and evaporation, well, you're going from a liquid to a gas. Yes, but it is two different things. Evaporation only happens at a liquid surface. It happens naturally. It's happening to water around us all the time. This is why if you leave some water sitting out in a tray or in a dish, it will eventually go away. It will eventually evaporate and be gone. And it's not that it's gone off into the air. Okay? This happens all the time. There's no energy needed. You don't have to heat it up. But if it is hotter, this process will happen faster. And it happens only at the very surface. The particles have to be at the surface. If they're in the middle of the water, they can't evaporate. And only a few particles can do this. Boiling is going from a liquid to a gas, but you're going to add energy. And while this happens at the surface, boiling happens closest to where the heat is, which is why when a pot of water starts to boil, where do you see the bubbles first form? At the bottom. And then they have to work their way up to the top. That bubble that you see is some liquid that has become a gas. It's just stuck at the bottom of the container until it can get up and through it. And the particles anywhere in a liquid can boil. Only the particles at the surface can evaporate. Okay? Questions? Wonderful. All right. Now, there is a thing. Yes, sir. Leave me your phone. Hurry up. There is a change that happens as soon as we put the word point onto these. When we change to melting point, freezing point, boiling point, and condensation point. Instead of a process, instead of something that happens, they now become a property. And what I mean by that is they are the temperature at which a solid becomes a liquid. They are the temperature at which a liquid becomes a gas. They are the temperature at which a liquid becomes a gas, or the temperature at which a gas becomes a liquid. That is a number, ladies and gentlemen. That is a number. That number never changes. You are either above or below that number, but the number never changes. So if I take ice out of the back and put it on the counter here, it will start to melt. Why? Because the room temperature is above the melting point. The melting point for ice is 0 degrees. The room is 20 degrees. Guess what? 20 is hotter than 0. Ice is going to start to melt. Now, I can't get it to freeze in the room. Why? Because 20 degrees is warmer than 0. But if I put it in the freezer in the back, the freezer part of it is below 0 degrees Celsius. Water starts to freeze again. Okay? So these are the properties that involve changing from one state to another. All right. So we're going to take these and we're going to organize them this way. You are the solid state when you are below your melting point. So take a look at everything in this room right now. Everything that you see that is a solid either cannot melt or is below its melting point. Okay? So if you are a solid, this pipe is a solid, not because it cannot melt, but because the room is not 2,000 degrees. The room is not hot enough to melt it. This can melt. It just isn't hot enough right now to do it. Okay? The plastic on your computer can melt. It just isn't hot enough to do it right now. Now, your desk is not going to melt. The top of it. It will burn. But the legs can be melted down. The plastic in your seat can be melted down. It's just that it's not hot enough to get those things to happen. Now, if you know what temperature this is, we can say, all right, we are below the melting point. The one thing we can say about things in the room right now is we're below their melting point. If you are above the melting point, higher than the melting point, if it has already melted, but it has not yet reached its boiling point, you're going to be in the liquid state. You're going to be in the liquid state. So the reason that this water, the reason that the hand sanitizer are liquids, is because 20 degrees, which is where the room is at, is hot enough to melt both of these, but not hot enough to boil them. not hot enough to boil it. So we are in between these temperatures.
I got a question.
Go.
If you leave water out for too long, wouldn't it just evaporate though?
It does. That's different though. That's different. You're right. It will evaporate. Absolutely. But the reason it's a liquid right now is because it is not hot enough to boil and it is too hot to freeze. So you're in between them. Okay? So now we're putting an actual fact to these things. And if you get above the boiling point, ladies and gentlemen, you are a gas. So the oxygen that we are breathing right now, the reason we are able to breathe it is because it is above its boiling point. Now its boiling point is really low, but we are still above the boiling point, and that's why it's a gas. So again, people think, well, something's a solid, a liquid, or a gas. No, something could be a solid at one temperature, a liquid at another, and a gas at a third. Because it all depends on what the boiling point and the melting point are. All right, so let's use water as an example, ladies and gentlemen. Water has a melting point of 0 degrees Celsius. It has a boiling point of 100. If I have water in a container and the water is at 65.3 degrees Celsius, what state of matter is it going to be in? Is it going to be in the blue, the green, or the red? Where does this temperature go? Does it go below here, in the middle here, or above here? It goes in the middle. So guess what? That water is going to be a liquid. Water is going to be a liquid at that temperature. Now you said something interesting earlier, Fantasia. We talked about adding heat to this pipe, and you said it would melt. And that is true. It can. But only if it gets to the temperature where that happens. So water can be a liquid from 1 degree Celsius to 99. Okay? It can be a liquid anywhere in there. So when you add heat, it doesn't automatically start to boil. It has to heat up first. It has to get to the next point, that boiling point. All right, so let's use water as an example again. This time, what state of matter should water be at room temperature? 20 degrees. What state would it be in? Come on, what state is the water in this room? Okay, why? Why is it a liquid? I'm agreeing with you. Why?
Because it's not all the way frozen, but it's not all the way liquid.
It is all the way liquid. I guess here's what I'm looking for. With what we're talking about, the reason it is a liquid is because we are above the melting point, but below the boiling point. So if we're above the melting point and below the boiling point, anything will be a liquid. I don't care what it is. Anything will be a liquid. Okay? Anything will be a liquid. So we can describe the state of matter based on these two things, based on melting point and boiling point. It's a solid because of this. It's a liquid because of this. It's a gas because of this. Let's take a look at one more. Let's use iron as an example, like that pipe. Iron's melting point is 1,538 degrees Celsius. Far different from water's. Water's was 0. Very different. Boiling is 2,861 degrees. So what if you have iron at 1,300 degrees? What state of matter is the iron going to be in if it's at 1,300 degrees?
Solid.
Why? You're absolutely correct. Why?
Because it's not at a boiling point.
Okay, it is not at the boiling point, but it's also not at the what?
Liquid.
Also not at the melting point. So, since we are not hot enough to melt, we are going to be a solid. We are going to be a solid. The only way it can be a liquid is if it is in between these two temperatures. If you're lower than this, you're a solid. If you're above this, you're a gas. It's going to be a solid. Okay? Same example. What if our iron is at room temperature, 20 degrees Celsius? Adon, what state of matter is it going to be? So you're telling me 20 degrees goes right in here between these two numbers? Adon, 20 degrees is between 1538 and 2861. Where does it belong? Below this, between these, over this.
Over.
So you're telling me 20 degrees is bigger than 2861. What I'm asking you, Adon, the number 20, is it less than this? Is it between these? Or is 20 bigger than this number?
Yes.
Less than which?
Then the 15.
It's over here, right? So what state is that?
Solid.
There you go. That's what we're looking at here. That's what we're looking at here. Since 20 is less than the melting point, it's going to be a solid. If you are below your melting point, you have to be a solid. Your temperature is below your melting point. All right, let's take a look at oxygen. Oxygen gas. The melting point for oxygen gas, minus 218 degrees Celsius. It's got to get really cold. The boiling point, minus 183. Oxygen is at minus 240 degrees Celsius. Where does negative 240 go? Is it less than 218? Is it more than 218 but less than minus 183? Or is it more than minus 183? Where would minus 240 go here, Allison? In the blue, the green, or the red? Where would that number go? So it would go here. It's bigger than minus 183. So just so we're clear, I'm talking about this number right here. Is this number, and you don't need to know anything more than it, is this number smaller than this one? Is minus 240 smaller than minus 218? Okay, I'm going to try to put this another way for you. Okay? You buy something, right? And you owe someone $240. You're minus $240. You owe someone $240. Okay? Is that more or less than owing somebody $218? If you owe someone $240, is that more or less than owing somebody $218? Okay, so then that goes over here. We are lower than this temperature. And I know the minuses confuse us, right? So this would be a solid. It would go here, ladies and gentlemen. Okay, same example. Okay, if you're at 20 degrees Celsius, sorry, my numbers didn't come in here. There they are. 20 degrees Celsius is above minus 183. Therefore, it's a gas. Why? Because we are above the boiling point. We are above the boiling point. Questions, ladies and gentlemen? All right, one last one. Gold. You can melt gold, ladies and gentlemen. Gold melts at 1,064 degrees. It boils at 3,080. Could you imagine boiling gold? turning it into a gas, watching it just go off into the air. That'd be terrible. Terrible.
They'll probably get in your lungs and then damage it.
Could. What state of matter would gold be in if it was at 3,163 degrees Celsius? So it's in between these two? It's below this one or it's above this one? So that number, 3163, if this were a number line, where would it go? It would come over here. It's higher than this temperature, right? This number, 3,163, is bigger than 3,080. So it goes over here. It goes over here. It would be a gas. It would be a gas. Okay? Sorry. Last one. Rubbing alcohol. You know the stuff you put on a cut, things like that? Rubbing alcohol has a melting point of minus 89. There are some people, ladies and gentlemen, who store alcohol like vodka and things in their freezer. And it doesn't freeze because it has a melting point or a freezing point much lower than the freezer gets down to. Your freezer is meant to freeze ice to water. Freeze water to ice, I should say. So what it does is it's set for about minus 4, minus 5, minus 6 degrees Celsius. Just enough to freeze water. If you put other things in there, it will not freeze them. Some it may, some it won't. Alcohol, it won't. Alcohol also boils at 82 degrees. It boils before water will.
So I got a question. Can you actually freeze oil or no?
You can, but the question is what temperature do you got to get it to?
No idea.
Well, that's the thing. It depends on what kind of oil, and you would have to look it up. But it has a freezing point, sure. So if you had alcohol at minus 45 degrees, where does minus 45 fit? Is it less than minus 89? Is it between negative 89 and 82, or is it above 82? Minus 45 is bigger than minus 89. Nope.
Why is it not a gas?
Because is this bigger than this number? It is. Remember, we're talking about minuses here. The bigger the number minus, the smaller it is. So minus 50 is smaller than minus 25, right? I'm trying not to confuse you, but I need you to kind of think about this. Okay? So minus 89 is more negative than minus 45. Minus 45 is not as hot as 82.
Oh,
So it goes in the middle here. So it's a liquid. Questions? All right, that's what I got for you for today, ladies and gentlemen. In Canvas, you have got an assignment, ladies and gentlemen. You can spend the rest of the hour working on it. You got 12 minutes to get it done. It is in the modules. It's the states of matter worksheet right here, ladies and gentlemen, not the one with states of matter and temperature, just states of matter. You click on it. A substance that has a definite shape and definite volume. You tell me if that's a solid, liquid, or a gas. Substances where the particles are moving slowly. Is that a solid, liquid, or a gas? So on and so forth. Now, please listen. Here is the part that people don't do, and I don't give them credit for the homework. Everywhere where it says replace, you are going to replace this with a term. Water has a blank of 0 degrees Celsius. What is that for water? It's what? Freezing point. This is when it will transition from a, freezing is going from a what to a what? This is when it will transition from a what to a liquid. What will it go to? From what to a liquid at 0 degrees Celsius? What state will it be in? Solid, liquid, or gas?
Solid.
To a liquid through the addition of heat. So that is what you are doing here. You are replacing these with the proper terms. Okay? And then here, explain the differences between crystallization. I should have used freezing and condensation and list the similarity between the two of them. Okay? So tell me something that is the same about freezing and about condensating. And you will find it in those tables that I gave you, in those diagrams. So tell me a difference between melting and freezing point. Tell me a difference between freezing and freezing point. There you go, ladies and gentlemen. That's your homework. If you have questions, please raise your hand, call me over, and I will be happy to help you. Otherwise, ladies and gentlemen, let's get to work, please. Well, you want to do well on the test, then it affects your grade. Yes.
How much of it?
I don't know. It depends on how well you do on the test because you did this or not. Solomon, do you play any sports?
No.
None? I can believe that.
Why?
Well, because then you don't understand the importance of practicing.
I understand practicing. I just don't like it.
Well, nobody does, but how do you get better at something?
Just doing it.
So just practicing.
Yeah.
Okay, good. Practice then.